origin. So I picked the hardest of there's three things you're supposed to do here. The moment of inertia about the x-axis, moment of inertia about the y-axis, and the moment of inertia around the origin. If you can get the x and the y, you've got the origin. So the x-axis, though, that's the hardest one. The reason is because of this. That is a problem. Well, I guess this is a problem too, isn't it? But this is the bigger problem. Because when you take this and stick it in there, and you end up with x squared, y squared, and y to the fourth. Y to the fourth is the big issue. Because when you integrate y to the fourth, you get y to the fifth, and you have to plug in a binomial into y to the fifth. What a nightmare. But look, it took me, what, 5 minutes? And I got it right. So here it is, and I didn't even use a computer. So I suspect that some of you used computers. That's fine, especially with this. Now, you won't be able to do it on the quiz, but I tried to make the quiz one that wouldn't have this ugliness. But anyway, if you're curious what I did, I took y to the third and plugged in a minus x, and I used cubing a binomial to get that nasty thing. And I did the same thing, raising a binomial to the fifth power, you get this. And if you want to know how to do that so quickly, just have Pascal's triangle sort of memorized and go down to the sixth line. I know it's like got a 5 here, but it's actually the sixth line. It's 1, 5, 10, 10, 5, 1 is that line in the Pascal's triangle. Maybe cubing is a little bit easier to remember. It's 1, 3, 3, 1 are the coefficients. But anyway, once you get that sorted out, plug in your numbers here. And then, yeah, that was pretty ugly. I really was scared at this point that I would get something wrong, but I've already got independent verification that my answer was correct. By the way, at this point, notice that when you plug a into here, you're going to have a to the sixth, a to the sixth, a to the sixth. Every one of these is a to the sixth. And so I just was like, I don't care about the a to the sixth. All I care about are all those fractions, the coefficients. And so I've got those here. And then I very carefully, actually not so carefully, added them all together. And I got down here to 780ths. So yeah, that's what all those crossings out were. I was trying to keep track of what I had added and what I hadn't. But yeah, 7k a to the sixth over 180 is the answer to this one. If you did the moment about the y-axis, it's going to be far easier. I shouldn't say far. It will be easier. It won't be quite as ugly. And the reason is that if you do it, you'll have an x squared here. So here, I'll put this right. Let's use purple. So the moment about the y-axis, that thing becomes x squared. And so the integral, you'd be integrating, you'd end up with this, x squared y, or no, x to the fourth, sorry, x to the fourth y plus y cubed over 3 that you would evaluate from 0 to y equals a minus x. So this is the moment about the y-axis. So here you just have to plug a binomial into a cube. And I guess we did that. Just 1, 3, 3, 1 is the coefficients that you have to remember. And so that's going to be far easier. Let's not take the time to do that. Once you have both of those, though, add them together. You've got the moment about the origin. So spin that thing around, or this triangle, I guess, is what we have, right? So here's the origin. Rotate. See how much inertia you can generate or overcome. All right, was there anything else? So we got number 19 sort of squared away. I know it's not satisfying that I don't give you the final answer to the moment about the origin, but was there anything else, other things confusing with the mechanics of doing this, not the algebra? What do you think?
I'm just curious, like, how you come up with the density function for that.
Oh, yeah, so it says here that the density at any point is proportional. Once you see the word proportional, you got to say, okay, that's going to be a k. So here's rho is proportional to the square, okay, something squared, of the distance from the origin, or okay, from the vertex opposite the hypotenuse, and I've put that vertex at the origin. So I need to put in here the distance from the origin. So pick a point like xy. What's the distance that that point is from the origin? And that's the square root of x squared plus y squared. And then once you cancel out the square and the square root, That's it. So it's this translation of English to math. So I know we wish that everyone would just speak math, then we wouldn't have to worry about ambiguity, right? I believe that it's pretty clear. It's just understanding what does it mean to be proportional. It means that something is the same as something else, just according to like a factor, you multiply by some constant. And then the square of the distance. So now you have to think, okay, where is my point? What is the distance? It's this distance here. As long as you orient this with the that corner at the origin, it really simplifies this calculation. Anything else? Other things about this or about the others that we needed to talk about? Maybe the mechanics of or setting up, knowing what the density is. All right, I'm hoping, now I got to be honest, I have not triple checked this. I'm hoping this is easier. So I know it says to find all three of the I sub x and I sub y and I sub 0, but we all know that I sub 0, the moment about the origin, the moment of inertia around the origin, is just the sum of the two. So just do I sub x and I sub y. Oh, I blew it. No, that's not going to be easy. Why did I do this? Okay, I'm going to change it. Just a minute. Just give me a sec. Just a sec. Yeah, sorry. I don't know what I was thinking. Here, just a minute. Hold on. If you're watching online, just fast forward. Okay. Let me find the quiz. Yeah. Oops. That's statistics. Hold on. Yeah, I made a minor change at the last moment because I liked the picture better. And apparently, if I like the picture, it makes it nasty. Sorry. Yeah, I mean, seriously, I checked it and then I just made a minor change. I mean, it's not that minor, I guess, but here's the quiz. I'm going to change it though, don't worry. Switch this. Yeah, here we go. Import. Okay, so yeah, here. So let's ignore the picture for a minute. I'll pass this around in a minute. Don't worry. Let's ignore this and change this to just x squared. And then I need to have changed this to y equals 2. There we go. I think that works. Y equals 2x squared. Yeah, okay. So here, I'll show you the picture, and then I'll explain why I changed it, and then I'll give you the quiz. So here's the picture. So notice all I did is I flipped that parabola over. Y equals x squared. It was completely innocent. I thought it would be fun, but fun means hard. There's that. So this is the region, and this works out pretty nicely, to be honest. The other region up there does not. So, but I like the looks of the one up there, the blue one. That looks so much nicer than this. So I thought, oh, instead of having x squared, I'll change it to 4 minus x squared. Surely that can't change. But no, that would, yeah, you don't want to do that. Yeah, x squared. X squared is fine. Okay, so here, let me give you these. Oh yeah, we'll trade. 1, 2. Oh, let's start in the back because I always take lots of back row. Yeah, if you have extras, send them forward this time instead of back. There's a few. I don't know if there's too many. There's 1, 2. Yeah. Wait, what? This x. Oh, x equals 2. X equals 2. That's what I meant. X equals 2. It really doesn't matter. Oh yeah, maybe I would meant y equals. Doesn't matter. Let's use this one. Yeah, use x equals 2. So, oh, you want an extra one over there? Sorry. In this row, I neglected you. There we go. This. Oh, you got one. How'd that happen? Does everyone have one now? Okay, so just to be clear, this is the region. This is the region. Everything else is good. Just change to this. This is x equals 2. So yeah, so it's going to be y equals 0, x equals 2, y equals x squared. I think the other one, yeah, I think I should have, well, it's okay. Yeah, they keep changing, but let's go with this. Here, I'll fix it over here. X equals 2. There. Okay, I fixed it up on the screen, and I will fix the graph too. Good enough. Not this. Whoops. Okay. grab homework first, and then I'll come back for the quizzes. So don't rush too much, but you rush a little bit. So I should check what mine is as a decimal. All right, let's see what we have. If you're done, if you're not, try to wrap things up here. Fraction, good. I got fractions as well. You got a fraction? Okay, very nice.
So far, as we all compare, we all got that.
Okay.
If you got a fraction, you got it right. That's all I'm
I'll use yours as the key. That's correct.
Yeah. You get a fraction? I got a fraction. Then you got it right. I think we forgot that detail. If you get a fraction, you get it right. Get a fraction. Every other single person.
Well, I got fractions. I think I'm in pretty good shape.
I don't know. I know I got that in my mind. Maybe surprised when I got that.
You have fractions? Or do you use decimals? People do different. You got a fraction?
At the very end,
No,
of
he
the
says
first
you
part,
got a
it was
fraction.
like, I didn't add.
That must be. You did it.
At the very end.
Your fractions? Oh, you use decimals. But you use the fraction. All right, if you're still stewing over this, try to finish up. I'm going to come get it in just a minute. All right. Well, we'll see. All right, let's bring it in here. The last couple. Here we are. We're good. All right. All right, you got something? Well, you got the expressions. That's the important part here. Very good. Okay, let's see how we did. Wait, I've got them all, right? Okay, so let's see how we did. And then so here's the start. Now this is the important. I mean, it's super important to have the beginning correct, because if you don't have the start correct, you're not going to get the answer. So let's go over this really carefully. Is when you're looking at this region, we draw a rectangle. And so the delta x, the small side is, you could have done it the other way, but I think this is easier. And so the x values start over here at x equals 0, end at x equals 2. By the way, the outer limits are always constants. Always going to, well, constants or some parameter. And then the inner limits will be the top and bottom of this little rectangle. So we have y equals 0 is the bottom of this, and y equals x squared is the top. So if you didn't use those, then you were using a different region than me. So I saw some people had constants for both of them. If you did, if you went, here, let me get rid of this. If you did 0 to 4 for x and 0 to 2 for y, this was your region. So you did that big rectangle. So anyway, that's what you did? Okay, well anyway, so getting back to this, I'm pretty sure I got the moment about the x-axis correct because it compared well with many of you. So let's go through this briefly. Okay, good. Here's my answer. It's 224 over 9, which is the same as about 24.89. So this is after a bunch of, you can see, there's the work. Good enough. Okay, so I'm not so confident about my other moment because it does not compare to the to many of you. So let's find out what I did wrong if I got something wrong. This is the moment about the y-axis. So the moment about the y-axis, you throw in an extra x. My mistake might be that I just went too quickly. So I'm going to go more slowly. So throw the extra x in. Maybe I'll actually write this out. I didn't bother before. So this will be x cubed plus x squared y. Is that right? So this becomes this. Then we integrate with respect to y, and I get x cubed y plus x squared y squared over 2. So far okay? Okay, I'm doing okay. And these should be y's. I was being lazy. But those are values for y. I'm going to plug those in. Now I'm going to plug in the limits, upper limit minus the lower limit. The lower limit 0 ends up being 0. So I'm leaving that off, but you should at least do it in your head because sometimes the lower limit is not 0. Well, if the lower limit is 0, sometimes it's, like cosine of 0 is 1. But anyway, let's plug that in. Here's what I got. So this is after plugging in x squared. So this is x cubed times x squared. This is x squared times x squared squared, x to the 6th. So far, okay? Okay, now I do the integral of this. Let's see. So the integral of x to the 5th is x to the 6th over 6. Oh, there it is. I left off my 14 here. There's my mistake. Okay. This should be a 14 here. Okay, see? So I was doing it way too quickly. I was trying to rush so I could be done. Sorry about that. Okay, so this is correct. Let me fix the rest of mine now that I've got that. I think what do I lose? 10 points? Okay, more than that? Lose 20 points? 50? Okay, I'll grade yours the same way. If you make it, no, it's -1. Okay, okay. So it's just a 1-point error. Good. But anyway, getting back to here. So no, actually, it should at least be 10, I think, out of 100, because that's a pretty fundamental rookie error, right? You're not dividing by 7. Okay, but anyway, hopefully you didn't do that. Let me fix the rest of this though. So instead of having 64, it should be 64 over 7. So that should be over 7, and this is no longer correct. Let me get rid of this. So let's see, this is going to be 21sts. So 21, so 7 times 32 plus 3 times 64, whatever that is. So I'm too lazy to figure it out right now. But that's going to be the correct answer here, apparently. Over 21. Okay, and then this isn't correct either because I have the wrong moment about the x-axis. But you'd stick that in here to get the moment about the origin. But I'd said just have to do the 2 moments, not the third one. All right, so we found my mistake. Hopefully we can find yours if you made mistakes. So, sorry about that. All right, we need to move on though. What are we doing today? We're doing surface area. This can't be that hard. So let's deal with the surface area. The big idea. The big idea, just like in all of calculus. It's been a while since we've done this sort of thing. So let's take it slow. So the big idea is that we want to compute something. What we do is we start by finding a way to approximate that thing. So I want to find the surface area of some object, like this chair that has, it's not a flat, the back of this, it's not flat, it has some area, that it's curved. So I want to find the area for that. So what we're going to do is we're going to start by finding a way to approximate it. Usually the approximation is going to involve things like straight lines. If you have a curve, you approximate with a straight line. If you have something like this surface, we're going to approximate it with little like rectangular pieces, because I can find an area of a rectangle. It's hard to find the area of a curved surface though. So we're going to break it up into small pieces, find some way to approximate. Then we're going to add up a bunch of approximations to make a better approximation. So in other words, if we can approximate this with like one big rectangle, then maybe we could do it with 4 smaller rectangles, and then maybe 16 little rectangles. You can see where we're going with this is make the rectangles smaller and smaller. Things get better and better. And of course, then we introduce a limit, take the limit of the sum of the approximations to get the exact value. And that limit is going to employ the fundamental theorem of calculus, my favorite theorem in all of calculus. And often the limit ends up being an integral using the fundamental theorem of calculus. So bear with me for just a minute. I'll show you a couple of pictures to see how we're going to approximate, but we'll get to the formula. That's what you really care about, I know. So here's the idea. Here's the picture is you've got this surface, and you've got this thing up here, and we're going to say, okay, this will be approximately the area underneath it. And I realize it's not perfect, but it's not terrible. It's close. It's not going to be exact. Now that, unfortunately, isn't a rectangle. I mean, if you think about it, because this thing is not existing, it's directly above this rectangle here, or this square, but because it's tilted, it's kind of askew, it's going to be a parallelogram. So the area of this thing is in a parallelogram. Seems like we had some vector stuff that helped us figure out areas of parallelograms. Wasn't it the cross product? The cross product of 2 vectors, that's what it was. The cross product of 2 vectors ends up being the area of the parallelogram. So I think you can probably guess what's going to happen here is we've got this picture. Let's get just that part that we care about. So if you look at that and just zoom in on the pink thing, here's the pink thing. That we have these 2 vectors. Those vectors are going to be the slope of the surface in the x and y direction. So for example, the A vector, that's really annoying that it just keeps moving. Let's see if I can do this without touching. No, that's going to be imprecise. I'll touch it once. Darn it, why? Okay, I won't zoom in. Okay, so the A, that is going to be related to f sub x. And the B, that's related to f sub y. Now, it's not f sub x and f sub y because notice that this has been scaled to be the same size as delta x. So we have to scale f sub x and f sub y. But it shouldn't surprise you that we're going to be doing derivatives. And then once we have those derivatives, we're going to be doing a cross product of 2 vectors. And then once we have that cross product, we will do the magnitude of that resulting vector. So let's see, how much of this do I want to make you suffer through? Because there's the derivation, which is fascinating for me, but painful for you, probably. So let's see, I've got that. Here we go. So let's just do this. You can gaze upon it. Here we go. Yeah, the area of the parallelogram, we already know that. I know it's black. I don't know why it turned black. I don't know how to get it back to be white on a black on a white background, but whatever. So we're going to take these 2 vectors, and now here are the vectors. This vector is the vector that I had called A on that previous picture. I'll show you the picture again. And this vector is the vector b. So you might wonder, how do I know it's this? Well, we'll notice that we've scaled this vector. So you have the slope in the x direction. That's the slope is rise over run. So if we go over delta x, we're going to go up or down by delta x times the slope. So the same thing goes for the vector b, which is the slope in the y direction. Let me just show you the picture again so you can see. So vector A, you're going in the x direction. Delta x is how far we've gone. How far up and down we've gone is the f of x, or the f sub x times delta x. And same thing goes with the f sub y. So getting back to this nasty thing that's dark and black, I don't know why. So I did the work for you, okay? So like I said, we're going to get to where you care. You probably don't care about this. So here we've got all of this, and then we've got all of this, and this is the, well, we're almost to the important stuff. You're still not caring, some of you. So the last bit, and this one turned green, I don't know why. Do I want to show you that? Yeah, why not? Yeah, I'll do it. Yeah, there it is. Okay, I know, it's yeah, you can't even read it. Never mind. Let's go back to this one. Yeah, I have no idea why I did this, and I should just retype it. And then I wouldn't, but oh well. Okay, so here's the deal. It's that bottom line. I'm going to redraw the bottom line here. Let's just go to Notability. That's going to be so much nicer in just a sec. So it's that bottom line that I care about. Copy and delete. Give me a sec. Go back to Notability where I like the way that things work. There we go. Okay, so there it is. I know you can't see it, so I'll write it here. So this thing here is this. It's the square root of f sub x squared plus f sub y squared plus 1. That's the magnitude of the cross product of those two vectors, the a and the b. And then you have the, delta x, delta y. That's very important. So what we're going to be doing is that's going to be the area of one of these little scales, if you will. If you can imagine this surface covered with little parallelogram shaped scales that stick out from it in various directions. That's just one of them. We're going to add up, and I'm going to do a double sum because you're going to be adding in the x direction and the y direction. So I'm not going to write down limits here because I think that we're not going to worry about that at this point. But this gives us a hint as to what's going to happen is when we do the limit as delta x and delta y gets to 0, this thing becomes an integral, a double integral in fact. And so this thing ends up being, so this is the fundamental theorem of calculus squared. And it becomes a double sum. So the square root of f sub x squared plus f sub y squared plus 1. dx dy. It doesn't matter what order. You know, you're going to adjust the order. I only have dx dy because that's the delta x, delta y in that order. But that is it. That's the, I'll put the PowerPoint back up here, but that's where the surface area formula comes from. This should look somewhat familiar. You might say, why is that familiar? Well, here, let's get the surface area up here. Oh, sorry. Anyway, yeah, this is from the textbook now, and it got cut off there for some reason. So here, I'll just fix it up here maybe. Anyway, yeah, so yeah, it should look similar to something you're familiar with. And the thing that you're familiar with is arc length. So let me just fix this so that it's not bleeding over. Here it is. Here we go. There, and this. There. So it'll update here in a sec, hopefully. We're waiting for the magic to happen. It's not going to be magic. Oh, there, it updated. Okay, yeah, so here it is. This is the surface area. So surface area, area of a surface, is a double integral of this thing. And this, I've just rewritten it, or at least the book have rewritten it in terms of z, because z is the function, I'll write it up top, is you're familiar with writing things like this, hopefully, is a function of x and y. And so the partial of z with respect to x could be written like this, and the partial of z with respect to y could be written like that. That's pretty much it. All we're doing for our homework is just exploring this, and we're going to explore it a little bit here. So let's see. As you can imagine, though, I don't know if you have memories of doing arc length, but arc length back in Calc 1, did you do arc length in Calc 1? I don't know if you did. We have certainly done arc length in here with, what is it called? The polar coordinates, as well as using parametric curves. So even if this isn't as familiar, you could stick the dx over dt and dy over dt, and then it'll become more familiar. But let's go and do this with this surface area. And as you can imagine, because of the radical, things are going to get ugly really quickly. So let's try an example of this. I'd like to find, let's see, we'll just do two examples. So I have this surface, and I am going to see how much of that, what the area of that surface is above a triangular region in the plane. Let me just get rid of the pen markings there. Here's a picture, if it helps you. Whoops, where is my picture? There it is. Oh, wait, where's the original picture? Oh, I don't have the picture of the region. Oh, here it is. Here's the region. There, I knew I had the region. Or no, the surface. So this surface is a surface that's kind of poking out at you, curving upward, and you have this triangular region that's above this. So let's actually do this. It's kind of, yeah, that's okay. You can ignore, let's see. There, we'll just do this. And then we'll do it ourselves, even though I've got it typed up. It's much more fun to do it carefully. Okay, so first things first is we want to sketch the region. You know the deal. Just like any double integral, in order to do it correctly, you're going to sketch the region. On Friday, when you do these double integrals for me, you're going to sketch regions. So every one of them will have an XY axis for you to sketch a region. So let's see, 0 to 1 for the X direction. So this is X. Sorry, my one kind of funky looking. Let me fix it. This is 1. And then Y goes from 0 to X. That's here. There. Wait, I did that on the wrong side. Y goes from 0 up to X. There we go. Okay, so here is the region that we're interested in. Okay, so far so good. Now we're gonna set this up as a double integral. Let's use a vertical rectangle to start, and we'll see if this is okay. If it doesn't work out, then we'll switch to a horizontal rectangle, but I think this will work out. So I'm going to set this up like this. Ooh, this is good practice. See if you can come up with because some of you are still struggling with the limits on a region like this. So just take a minute, jot down what you think the limits are, inner limits and outer limits. Sometimes it's helpful to remember that since this is with respect to x, the outer integral, you're going to have x's here. And because the inner integral is with respect to y, you're going to have y's there. And so we just have to fill in the correct stuff. So let's see if you got it right. Y equals 0 is the bottom. That's the bottom of this rectangle. And y equals x is the top. For the outer integral, you have constants. These will always be constant for the outer integral. Never will you have x equals y. Some of you did this on some previous quiz. I forget which one. You can go dig them out. Some of you, I know you're concerned that I'm not doing my weight training. Well, I appreciate it, but I'll try to pick up that maybe over the winter. I'll do a little bit more, a few more curls or something. But anyway, so those are constant. You can go get your quiz, is what I'm saying, and it might help you to look at that before Friday. So it's the little pro tip. Take a look at the quizzes because the test will be similar. Okay, so far so good. We got the setup. Last things last. Last things we got to do is find the derivatives. So I'll just put a 1 here. 1 plus. Now I need the derivative in the x direction squared and the derivative in the y direction squared. So let's go up here. Here's the function. The derivative in the x direction is 2x, and the derivative in the y direction is just 2. So this is just a problem from the book, and I see that they were kind to us because notice that when you get done with this, there is no y. There's not a y in this integral, so the inner integral at least is going to be simple. So let's go ahead and do this. This one won't take too long, hopefully. So we have the square root of 5 plus 4x squared times y, evaluated from y equals 0 to y equals x. Okay, double check my calculus. So the calculus and maybe a little bit of algebra thrown in there. Make sure I got it right. But do ask if you're confused about, like, why is this y equals x? Why is that the upper limit? I'm suspicious that some of you have no idea because you're not setting up your limits correctly on these things. So please do ask if you're still confused. And pay special attention to those limits for the test on Friday. I think I've got a practice test up. If not, I'll put one up later today. Okay, so far so good. We got this. Now the rest of this is just, calculus. 0 to 1. So this is going to be x times the square root of 5 plus 4x squared. Look at that. I can do that. No problem. U is equal to 5 plus 4x squared. Du is equal to 8x dx. So I'm going to rewrite this to be like this. 1/8 times the square root times 8x dx. This is another place I think some of you are struggling, is maybe with your substitution. So basic substitutions like this, you should be able to do pretty quickly. I sometimes neglect to write out all my parts of it, so I'm gonna try to be better. So there's that. So do ask though if there's a question. Okay, I'm just going to change colors because we're changing to U. I should have put that in. So this is going to be here. So 1/8 times the integral of the square root of U du. Notice that that is du. Isn't that brilliant? Okay, we got the antiderivative. You can all do this, I hope. So this is 1/8 times 2/3 times u to the 3/2. No evaluation yet because I have to change it back to x. I know you could put a c in here, but why bother? This is a definite integral. Okay, let's go back to x now. So this is 1/8 times 2/3 times 5 plus 4x squared to the 3/2, evaluated from x equals 0 to x equals 1. I need to make sure my test is this easy. And all the problems I do for you, in here. Because this is just 9 to the 3/2 minus 0. Look at that. I mean, so easy. That's 27 twelfths. So you can cancel, what is that, 9/4? Did I get it good? Did it do okay? What do you think?
You're adding 5.
Oh, it's not 0. Look at me. I did. There's such a rookie mistake. Thank you, Joshua. Oh, I can pretend that I did that on purpose to show you the dangers of just doing that. Oh, but I didn't. I did it completely without thinking. 1/12 times 5 to the 3 halves. Oh, what a ripoff. I lost it. Okay, that's okay. I will regroup. Okay, very nice. So this is going to be 5. It's not quite as nice. I was so excited that it was going to come out to be a nice number. It's still pretty good. 27 minus 5 radical 5 over 12. That's not bad. All right. Now I've got it right? Okay, good. Okay, we got to do one more, at least set up one more so that you can see, because the homework, you'll have, I think, one that's like that, and there's one that's not quite as nice. Okay, so let's find the other example. Let's see, where is it? No, that one's too easy. Here it is. Is that good? This one I don't like either. Just a minute. There's got to be something better than this. Thought I had something slight. Oh, here it is. Oh, I just didn't scroll far enough. This is it. Okay, what about this one? Find the area of this surface that's inside a particular cylinder. So you can kind of imagine this is a paraboloid. You got this paraboloid, and you have a cylinder cutting it, and you want to know that piece. What does that look like? I'll bet you can guess how we're going to do this. You know, what technique we're going to use just by looking at these functions. You got lots of x squareds plus y squareds, probably going to use polar coordinates. So give me a sec. We'll get this set up, even if we don't finish it. I want to make sure we have it set up so that you can see how to do these. Copy and delete. Come on. Oh, did I put something on? I don't know if I'll check. I don't know if I added to your homework or not. If I didn't, I'll do that after class here. Okay, so first things first, we have to think about what this region looks like. Well, we're inside the cylinder, so that means that we're inside a circle. If we look at this from the top down, it's like we've got an apple corer, and we've cored this surface, and we're just looking at this circle from the top. And of course, that's not it's a bowl shape is what you'll end up with, but this is what we're going to end up with, is that from the top. So our double integral, let's see, I'm just going to call this the region. So over the region, we'll call this R for now. And let us get our integrand, and then we will convert this to polar coordinates. So let's see, dA. I'll just go with dA. So we'll get, because obvious, I don't know if it's obvious to you, but anytime I see a circle as my region, it's going to be way easier in polar coordinates. So let's see if we can do this. We need to do the set up this thing. It's going to be 1 plus, let's do the derivatives. F sub x is 2x. F sub y is 2y. So you're going to have 1 plus 2x squared plus 2y squared. So far, so good? All right, now let me just simplify that just slightly, and then we'll convert to polar coordinates. 1 plus 4x squared plus 4y squared. There. Okay, so that's what we're using. And now let's convert this to polar coordinates. I mean, it's pretty straightforward because it's a nice circular region. So this thing ends up being the integral from theta equals 0 to 2 pi. R goes from 0 to 10. And then we have the square root. Now bear in mind that this is 1 plus 4 times x squared plus y squared, which is 1 plus r squared. Don't forget to throw in an extra r because we just converted to polar coordinates. And then dr d theta. Oh, 4. Yeah, 4r squared. Sorry. I was so excited about my r squared, I forgot my 4. There we go. I think you probably can see what's going to happen here in terms of the using substitution, if you let u equal the stuff inside the parentheses, it's almost exactly the same substitution we had, where you have 8 times r times dr for the substitution for du. So this one won't be terrible once you get it set up. Yeah, what do you think, Daniel? Yeah? Oh, yeah, what do you think?
Don't you need the sine and cosine in there? Like the r times sine of theta and the r times cosine for the x and y?
We could do that if you want. That's going to be more painful. Here, let me just show you what I mean. So here, I'll just go down here. So we're converting this. So yeah, we could do it that way if you prefer. I'm just gonna get started because I don't want to do it that way. So r cosine of theta squared, and then 4r times sine of theta squared. Anyway, if you do it this way, notice that you have a 4 and an r squared in everything. You can factor that out. You'll be left with 1 plus 4r squared times cosine of theta squared plus sine of theta squared. And it gets you the same thing as what we had, because that's just 1 there. So yeah, anytime you see this, instead of using sines and cosines, just remember that x squared plus y squared is r squared. It's much simpler than going through, but you could do it that way, and there's nothing wrong with it. It just involves a few extra lines. Is there anything else before we, well, actually before we finish? We're going to have to finish. All right, well, I guess we're all done. So do look online for a practice test. I'm going to double check that I have homework for you, and we'll see you in the morning. Let's see what we got here.